So hello everyone, this is lecture 11 for the nuclear physics. In the last lecture we have discussed all the related questions to the basic properties of nuclei, and today we will complete all the questions related to the radioactivity. So let's see. First question is given: A is disintegrating into B, B to C, and this is constant of disintegration, that is lambda A, lambda B, and we need to find the NB. So we need to find NB, and these are the options are given. So options are required sometimes to solve it. That how can we solve? So these four options are given. So you can see here that it is t to the power 1 only. So if we need to expand somewhere the exponential, then we will expand only up to the t to the power 1. So we already calculate the expression for nb, that is lambda a and not. You must remember this: lambda b minus lambda a, expansion minus lambda a t minus expansion minus lambda b t. So this formula we must remember. Now we will just expand it. So it will be, exponential x is simply 1 plus x divided by 1 factorial plus x square by 2 factorial. That's why it will give you 1 minus lambda a by t, lambda a t. So this is, we are expanding only up to the first term, that is t to the 1. Here also it will give you this. So this 1 will cancel out and you will solve this, you will get this. So this will be your answer. This is the first option. Next is, in a typical human body, the amount of radioactive 40K is this percent of its mass. So inside the human body, the amount of radioactive potassium, that is this much percent of the mass of the human. Find the activity due to the 40K in a human body of mass 70 kg in kilobecquerel. We need to find the activity, and T half is given for this K40, that is 3.942 multiplied 10 to the 16 seconds. And what is the activity? First we need to define this. So activity is simply the mode of this rate equation. So it is giving us the information that this minus means the nuclei is decreasing with time. But if you take the mode, then the whatever we will get, that disintegration per second, that is simply called the activity. So this mode is called the activity. So let's find the equation for activity first. At t equal to 0, activity is simply lambda n naught. Okay, so it is dn by dt, that is lambda n naught. And now at particular time t, at will be lambda n. So this will be lambda n. Now you know what is this, means n is simply n naught exponential minus lambda t, and lambda n naught which is described as a naught. So at will be a naught exponential minus lambda t. So this is the equation you must remember wherever you need to use the activity. So you will use this formula. Now you need to calculate the, what do you need to calculate? You need to calculate the activity, this. So for this particular time, so how you can solve this? See, this activity at particular time is given by lambda n. So you need to find the n at particular time, and lambda is, how can you find the lambda? So you know the half-life is simply log 2 by lambda. So lambda will be log 2 by half-life. So log 2, that is 0.693, and half-life for potassium is given 3.942 multiplied by 10 to the 16. Now how you can find the n? So n is simply means, it is mass is given. Mass is this percent of the human mass, that is 70 kg. So this percent of 70 you will calculate in the gram. Then that mass will be divided by the atomic mass, and that will give you the number of moles, and multiply the 1 mole nuclei. That will give you this Avogadro number. So you will get, it will give you the total number of nuclei present. So that will be you place here, and you will get the activity. That this will your answer. This will be 6 into 10 to the 3 disintegration per second, and 1 dps, that is disintegration per second, is called the 1 becquerel. So you need to find this answer in the kilo becquerel. So this will be 6 kilo becquerel simply. So this was a NAD type question, means numerical ability. You need to answer this in the single number. So answer will be 6 here. Now next is, a radioactive element X decays to Y, which in turn decays to stable element Z. The decay constant from X to Y is lambda 1 and Y to Z is lambda 2. If to begin with, there are only n naught atoms of X initially, at short time t less than 1 over lambda 1 lambda 2, number of atoms of Z will be, so we need to find the n3 exactly. So we already discussed this, and you can see the options is given in the maximum power t square. So we will expand exponential up to the t square wherever we will need it. So n1 is simply n naught exponential minus lambda 1 t. So we'll expand it up to the 2 terms. This will be simply expansion of exponential term. And n2 is this formula. We know this formula, so we will again expand this and expand this. So we have n1 and n2, and from here you can just solve this. Lambda 2 minus lambda 1, taken t common, minus 1 will cancel out, and this factor will cancel out, and you will get this. So you have n1 and n2, and n3 is simply n0 minus n1 minus n2. So this will be this, and this n3 will be this. So this will be your answer. Very easily you can find this. Next is, a radioactive material decays by simultaneous emission of two particles with respective half-life 1620 and 810 years. Calculate time in years after which 1/4 of the material remains. So see, this is your nuclei, some nuclei sample, and it is disintegrating into two particles simultaneously. So there were different half-life for both these particles like this. And this is your sample and this is disintegrating, and the constant of disintegration is lambda 1 lambda 2 into 2x and y. So it is simultaneously disintegrating. So at t equal to 0, initially it was n naught particles or nuclei of sample, and particular t it will be n, and dn by dt will depend on, means if it is lambda 1 for x, so it will be minus lambda 1, this rate it will be decreasing, and simultaneously it is also designating to the y, so it will be minus lambda 2n. So that's why you need to consider both of them. So it is simply minus taken common and lambda 1 plus lambda 2. So in the question, wherever this kind of question will be given, you just take in place of lambda equivalent, that is lambda 1 plus lambda 2. From here you can see it is simply minus lambda n, so lambda will be lambda 1 plus lambda 2. If you solve it, again you will get the equation which is kind of this, and here in place of lambda, it is simply sum of the lambda and lambda 2. So wherever you need this kind of thing, you just add them, and that will give you the equivalent lambda. And now we need to solve this, means when this becomes 1/4, so it will be n naught by 4. Now you can solve this, n naught will cancel out, and lambda and lambda 2 is given. So that is 1 upon 160, means this is half-life is given. So lambda 1 is simply log 2 by t half, and lambda 2 is half-life by means log 2 by half-life. So that's how you can just substitute the value. I can solve for time, that is 1080 years. Next is, in an ore containing uranium, ratio of uranium 238 to lead 206, nucleus 3. So at a particular time, this ratio is given with the uranium and lead. Kept the age of the ore, assuming that all the lead present in the ore is final stable product of uranium. So final product of uranium is, that is lead, and T half of uranium is given 4.5 to 10^9 years. So this ratio is given at particular time, Nu by NPV, that is 3, and uranium is disintegrating into the PV, that 238 to 208. Initially t equal to 0 n naught, and t at a particular n, that will be, and this lead will be n naught minus n, you know this thing. And now the ratio at particular time, so at particular time t, this is uranium n divided by n naught minus n, this must be equal to 3, and you need to substitute n is n naught exponential minus lambda t, and naught minus n is again this, so this will cancel out. From here you will get this equation, and you know this lambda is nothing but log 2 by t half, and t half is given. You will just substitute a value of this lambda t equal to log 4.3, so t will be 1 upon lambda, and lambda is this is log 2 value divided by the half-life log 4 by 3, and so you will solve this, you will get the time, that is 1.87 to 10^9 years. This is the average mean lifetime for the ore, okay, to convert ore to the lead. Next question is, nuclei of a radioactive element A are being produced at a constant rate alpha. The element has a decay constant lambda. At time t equal to 0, there are n naught nuclei of element. Then calculate the number of n nuclei at time t. So we need to find the rate equation. So initially n naught 0, at particular time n naught minus n, you know this. Now this time dn by dt, these are producing, means A is producing at the same time and it is decaying also. So producing will give you plus sign, that will be alpha, rate is already given, so alpha, and disintegrating is minus lambda n, so this will be your equation. Now you can solve this for 0 to particular time t and n naught to n. Simple log equation you can solve, and you will get n equal to this. So this will be your equation. Now second they ask, if alpha is given to n naught lambda, calculate the number of nuclei of A after one half-life. So after one half-life, we need to find the nuclei of A. So this equation we will use, this is n. So alpha is given to n naught lambda, and t is t half. So this lambda is nothing but log 2 by t half, and this t half also, so t half will cancel out, and you will get only minus log 2 here, so this will be 1 upon 2 from this, solving this, and just multiply this 1 upon 2 inside, and you will get this lambda will cancel out after taking common, and n will be 3 by 2 n naught for this. And also the limiting value of n, means what happens if t tends to infinity. So if t tends to infinity, you will see that it is exponential minus infinity, 1 upon infinity, and that will give you 0 to this. So it will be alpha by lambda, and alpha is 2 n naught lambda, so lambda will cancel out, answer will be 2 n naught. Next is A to 280 day old radioactive substance, so an activity of 6000 disintegration per second dps, and 140 days later it becomes 3000 dps. So what you need to find is, what was the activity initially, A naught, okay. So this is given A naught, we assume it was A naught at equal to 0, and after 280 days it becomes 6000 dps, and after 280 plus this 140, these days after it becomes 3000 dps. So you will use this equation again. I told you that wherever activity will come into place, you will use this equation. So just take this, means what will remain constant in whole this process, that is lambda will remain constant. That's why we'll take this equation into the lambda. So lambda from here it will be 1 upon t log a naught by a. So 1 upon t1 log a naught by a1 equal to 1 upon t2 log a naught by a2. So 1 upon 280 log a naught by 6000, and now this time is after this will be added to it, to this it will be 420 days log a naught by 3000, and here from here you just solve this. It will be 1 upon 2 1 upon 3, and you will get this equation, and you can easily solve. A naught will be 24,000 designation per second. So that's all for today for the radioactive questions. In the next lecture, we'll start the nuclear reactions. So you must see this lecture again, because there are a lot of questions which is asked from the this section a lot. Okay. So thank you everyone.